If you remember back when we were looking at kinematics, we saw that for a velocity time graph, the area underneath that curve had some physical significance. In fact, it was equal to the displacement. Well, let's recall that the way you found the area underneath the curve, um, you could approximate it, or you could actually do the thing that we called anti-differentiation, which, if you remember, that meant increasing the power by 1 on the variable and then dividing by that new power. Um, so that's what we're looking at here today. We're just kind of reviewing that. So let's say we have this curve, v equals 1/8 t squared plus 1, and I want to find the area underneath it. So I could approximate it by making a bunch of rectangles underneath and add up those areas, and I get approximately 5.75. Of course, that's going to be on the low end because you can see those triangles up there. There's kind of a gap. So we can do this again. This time, maybe make the rectangles a little bit bigger than they really should be. And now, when we figure out the area, it's 7.75. So again, that's just an approximation. It's a little bit high in this case. We could kind of look at half intervals, so increase the number of rectangles. Or we could also look at, instead of going a little too high or a little too low, we could have it cross right at the midpoint. And that's what we're doing in this case. We could add up all those areas, and this one's going to be a pretty good approximation, but it's not going to be perfect still. And we get an approximate area of 6.625. And again, we could try it with maybe more rectangles and add up the area, and we'll get 6.65624. But again, these are all approximations. We're getting closer and closer to this, but it's still approximation. Well, these are good ideas. What if we were to take the delta t interval, so we tried it 1 second and then we tried it down to half a second. What if we made this interval, this thing, as small as possible? So in other words, find the area. So this would be the velocity times the time. That would be the area of one of these rectangles, the velocity times the time. But have the delta t go to 0, the limit of that. And I'm going to add up all those rectangles. That's what this summation symbol means, to add them all up. Well, if we did that, we're going to get a really close approximation for the area underneath that curve. And in the limit where we have an infinite number of these rectangles, it's going to be exactly equal to the area of the curve. And when we do that, take the limit as the number of rectangles goes to infinity, this summation symbol gets kind of stretched out into this summation symbol, kind of looks like an S there. And this is back to that calculus idea, except instead of calling this anti-differentiation, which it will be the same thing, same method, we're going to call this integration. So integration is the exact opposite of differentiation. Integration is going to be just like anti-differentiation, something we already know how to do. Okay, so we're going to integrate. We're going to sum up all those rectangles as the number of those rectangles goes to infinity of 1/8 t squared plus 1. This symbol here is called the integration symbol. This is the lower limit of integration. We're going to be starting at 0, and we're going to sum it up all the way to 4. So we're going to be summing up all that time, little time intervals. This right here is called the integrand. That's the equation of the curve itself. And this is the variable of integration. So we're integrating, we're summing it up over these small little elements of delta t. When we take the limit of those rectangles going to infinity, instead of being an uppercase delta, the triangle symbol, it becomes a lowercase delta. It looks like this d. This is called a dummy variable because the answer does not depend upon the variable chosen. So I'm not really paying attention to this dt here. I'm looking at the integrand, which is the equation of the curve, and I'm going to be doing anti-differentiation. So if you remember with that anti-differentiation, it's just the opposite of differentiation. We're going to be increasing the power of the t by 1. We'll come back to that in a second. Let's look at another curve. We have y equals x squared. We want to find the area under this curve from 1 to 2. So in other words, this region right here. So what would this look like? Well, we have the summation from 1 to 2 of the curve itself is x squared, so we integrate x squared dx. Again, we're going to be summing up all these little tiny rectangles underneath the curve. So what would this look like? Well, let's do anti-differentiation on this x squared. As you remember, hopefully, that you increase the power by 1 and you divide by the new power. So it's going to be 1/3 x cubed. I'm going to have to plug in these limits from 1 to 2. That's why I have 2 of these quantities, 1/3 x cubed. Let me plug them in right here. So it's going to be 1/3 2 cubed minus 1/3 1 cubed. So I get 8/3 minus 1/3, and I get the answer of 7/3. This first one here, 8/3, that's simply the area from 0 to 2. In other words, if I wanted to find the area from 0 to 2, that would just simply be equal to 8/3. And the area from 0 to 1, that would just simply be equal to 1/3. So if I want to find this blue region, I would subtract out this white region from the whole, and I get 7/3. Okay, so let's go back to the original. We have v equals 1/8 t squared plus 1. I want to integrate this from 0 to 4. In other words, I want to figure out the area underneath the curve from 0 to 4 seconds. I know the equation is 1/8 t squared plus 1. I need to use the idea of anti-differentiation to figure out what that formula becomes. So of course that becomes t to the 1 power higher, it's going to be t cubed, divided by the new power 1/3. I don't see a t here, so it's really t to the 0, so it's going to be increased to t to the first power, divided by that new power, so 1/1. And notice this integration from 0 to 4, it's done. We've already integrated. Remember, integration is the same thing as anti-differentiation. That's what I did here, anti-differentiation. Notice I don't anti-differentiate the dt. That's not really necessary. That's just telling me what is the variable I'm concentrating when I do my anti-differentiation. But I'm going to be going from 0 to 4, so I need to plug in the 0 and the 4, and that's why I have this here to remind me of the numbers I need to plug in. So I plug in those numbers. Well, I simplify first. And then I plug in the numbers 4. So it's going to become 4 cubed plus 4 minus, so it's always subtraction in between. Now I plug in the 0. And so I get 6.67 meters. And that's an exact answer. That's not an approximation. That's exact. So the exact area underneath here is 6.67 meters. So if you remember earlier on, we were doing approximations, and we got something pretty close to this. But this is an exact answer. Now we did all this stuff before when we did the anti-differentiation, but now we're giving it a new name. Anti-differentiation is the same thing as integration. It's the opposite of differentiation. Remember, differentiation is finding the slope. Like if I want to find the slope of this, I would differentiate, and that would give me the acceleration versus time graph. But if I have a velocity time graph and I want to find the displacement, that would be the area of the curve, I would anti-differentiate, or I would integrate. Okay, there are some rules for working with integrals. So one thing, if you're integrating from A to B, that's the same thing as doing negative from B to A. And if you think about that, that's because, remember, you plug in the B and the A and you subtract. So if you reverse the order, you end up getting a negative sign. If you integrate it from A to A, in other words, if you're thinking about your curve, you're going from A to A itself, well, that's the same point. That would be like area underneath a point. Well, there's no area underneath a point. It's a line there. That doesn't have an area. If you're integrating something that has a constant, so we have k times some function of x, well, that constant, whatever it is, will come out in front of your integration. In other words, it's just multiplying whatever when you do the anti-differentiation. It's just multiplying by that constant. And then lastly, if you're integrating from a to b or whatever, two functions summed up, that would be the same thing as integrating one of the functions and adding it to the integration of the other function. This works for subtraction as well.